Good morning. Let me just briefly discuss about the content of my previous lecture. So what we have seen previously is that what is the importance of solar cell and what is the importance of photovoltaic technology. And then we have discussed silicon photovoltaics. In silicon photovoltaics, I just made this point that with silicon, we make the simplest solar cell architecture, that is a semiconductor homojunction solar cell. And then we have seen what are the basic equations and the physical quantities that one need to consider when one studies solar cell. We have to always remember that there are very important physical quantities and circuit parameters which are required for solar cell or to analyze for solar cell, and these are rectification factor, ideality factor, and then contact potential, series resistance, shunt resistance, etc. And apart from that, when we discuss about the solar cell when it is under illumination, we get the parameters like short circuit current density, open circuit voltage, fill factor, efficiency, etc. So whenever we study a solar cell, we have to always analyze a solar cell based on these parameters. And then we have discussed that in order to trap more light, an anti-reflection coating on solar cell is important. Over and above, one can have a texturing of the solar cell, particularly when we consider a thick solar cell, which improves light trapping, and then also it increases the efficiency of a cell. And finally, we discussed about thin film solar cell. We have introduced thin film solar cell, its importance of thin film solar cell, and then we have discussed that in case of thin film solar cell, the important thing is that we cannot make a surface texturing, which is generally done by chemical etching process, and therefore one needs to trap light using another physical process which is known as plasmonic light trapping, and this is possible when we coat metal nanoparticles on thin film solar cell, and because of localized surface plasmon resonance, the light which falls on the solar cell get absorbed and the absorption enhances significantly. And due to this enhancement of absorption, we get better solar cell performance. In the present lecture, we will continue with thin film solar cell. To begin with, I will talk about the shortcomings of silicon solar cell, and then we will discuss about role of wide bandgap material in solar cell, and then I will talk about how wide bandgap materials are being introduced in thin film solar cell, and one particular example will be discussed today, that is a heterojunction thin film solar cell based on cadmium telluride and cadmium sulfide. So when we talk about thin film solar cell, wide bandgap thin film solar cell, basically there are some materials which we consider which are studied in research or used in research and development significantly. They are like cadmium telluride, cadmium telluride. Number 2 is CIGS. Number 3 are gallium arsenide. And number 4 are CZTS. So they are all wide bandgap material and they are used in thin film form in order to make a solar cell. And the advantage of these wide bandgap materials are that they are all direct bandgap materials, and as they are direct bandgap materials, their absorption is much higher as compared to silicon. So out of this, I will discuss today about CDT solar cell, the solar cell based on cadmium telluride. So let me just tell again what were the disadvantages of silicon solar cell. We remember that silicon solar cell has a major problem with absorption of light. Well, silicon is an indirect bandgap semiconductor, its absorption coefficient is low, and also its band gap is around 1.1 electron volt. So overall the absorption of silicon is much lower as compared to the wide bandgap materials that we have just now I told you. So therefore what we require in case of silicon solar cell, we require thick silicon wafer to fabricate a solar cell. And in my previous lecture I have shown that if we take a solar cell, silicon solar cell of 1 micrometer thickness, we have very low short circuit current. And if we increase it to 100 micrometer, because of higher absorption of light, we have almost 30 times enhancement in the short circuit current. Now the problem is that when we go from 1 micrometer to 100 micrometer, the material cost increases significantly, and that is a problem, one major problem with silicon solar cell. Although the silicon fabrication methodology and techniques are very well known, and I discussed in my previous lecture, and I have shown that how people fabricate a silicon solar cell starting from sand and up to panel. But because of this low absorption coefficient, silicon solar cell is a problem, and therefore it has higher cost. And therefore it is important to search band gap of materials in such a manner that maximum number of photons can be used for photogeneration. Okay, so this is the aim. So let us see what are the material people have investigated so far. So if you see this graph is plotted actually again the x-axis it is semiconductor band gap energy, and the y-axis is efficiency. So if you look at this graph, you start looking from this point. This is germanium, which is an element semiconductor. This is silicon, which is another and which is very popular as solar cell. But if you look at its band gap is around 1.1 electron volt, and then it gives efficiency around 25% or slightly below 25%. Okay. Now you come to other materials which are okay. Let us go to amorphous silicon, which I have discussed in the last class. When we incorporate hydrogen in amorphous silicon or hydrogenated amorphous silicon, its band gap is higher, however efficiency is less. So now I go to wide band gap materials like CUS, CDT is one which we are going to discuss, gallium arsenide, CDS, etc. If you look at their band gap values, they are quite high as compared to silicon. And if you plot for silicon if you plot the energy and momentum, then for silicon it is something like this. So this is valence band maxima and this is conduction band minima, and they are not in the same K point, their K points are different, and therefore it is indirect band gap material with a band gap energy of 1.1 electron volt. So now you come to cadmium telluride. This is a material which we are going to discuss. For cadmium telluride, band gap is around 1.42 electron volt. So this is conduction band minima and this is valence band maxima, and this is a direct band gap material. It is wide band gap as well as direct band gap material, and therefore CDT is advantageous as compared to silicon. In fact, if you consider 1 micrometer thick CDT, the absorption of light is approximately same as 100 micrometer silicon. Therefore, when you use CDT as a material, basically what you gain is 1/100th less material to be used as solar cell, and that actually reduces the price drastically. Okay. So we will see how this CDT material is grown, and you will see the fabrication technique is also not that much involved as it was in case of silicon. Okay. So now further on CDT as a material, if we look at various physical properties of CDT, there is a typical crystal structure of CDT which is cubic, having a band gap energy of 1.42 electron volt. Its lattice constant is 6.482 angstrom. Electron affinity is 4.28 angstrom. Absorption coefficient is quite high, 104 centimeter inverse. Refractive index is 2.76. Melting point is 1092 degree centigrade. Work function 5.7 electron volt. Hole mobility is 65 centimeter square per volt SV, and electron mobility is 700. So most of the properties of cadmium telluride, including its higher absorption coefficient, leads to a material which is a very good material for solar cell and can be used in thin film form because of its higher absorption. The only problem which one finds in silicon in cadmium telluride is that it is having higher resistance. So if resistance is high, the electron mobility is low as compared to silicon. So if electron mobility is low, the transport of carrier is not fast. So this is one drawback of cadmium telluride material. Otherwise, there are several advantages of cadmium telluride as a basic material for solar cell. So now let us look at the periodic table. Because when we talk about a solar cell, what we need, the junction solar cell particularly, what we need is an N-type semiconductor and a P-type semiconductor. And when we make a homojunction solar cell, in case of homojunction solar cell, both P and N junction are same material. Okay. And when we consider in heterojunction solar cell, P and N are different material. So now a question comes that why don't we make all solar cell as homojunction? Why to make a heterojunction solar cell? Because if we make all solar cell homojunction, the advantage is that we just fuse two materials which are same. P is also say silicon and N is also silicon. So that is homojunction. That is what we have discussed in the previous lecture. So we don't have any problem with lattice matching or lattice mismatch. Okay. When there are two different materials, then they have a different lattice constant, and therefore there is a lattice mismatch that may create a defect. This is one logical argument that why don't we use all homojunction, and people did try with homojunction cadmium telluride, both N type and P type cadmium telluride which are homojunction, but they did not find a good efficiency of a solar cell. The efficiency showed in homojunction cadmium telluride solar cell was quite less. Then what people did, they make an heterojunction solar cell where they used cadmium telluride as p-type material and cadmium sulfide as n-type material. Okay, cadmium sulfide has much higher band gap, around 2.45 electron volt, and immediately they found a huge rise in the efficiency, much better performance of the solar cell, much better circuit parameters. So I will come to this point again. What was the advantage of heterojunction? Okay. Then of course we should know that when we use homojunction solar cell, we have less defect, and when we make heterojunction solar cell, we have different interface made of different material and therefore more defect. But still one wants to study with heterojunction solar cell. Before that, let me just tell you how one get an N-type and P-type cadmium telluride. This is important. So in case of silicon, I have discussed and you have seen, you all also you know this is a very standard textbook knowledge. The silicon we make N-type by adding pentavalent impurity to silicon or dopant, and we make P-type by doping trivalent impurity. Here in case of cadmium telluride, if you look at that, there are two elements, one is cadmium and another is tellurium, CDT. So if you want to make N-type, what you need to do, you have to dope or replace cadmium by either aluminum, gallium or indium, and it becomes N-type. Okay. Or you replace tellurium by fluorine, chlorine, bromine, iodine, etc. Iodine, etc. Okay. So in both the ways you can make an N-type cadmium. Okay. So these are the appropriate dopants for making N-type cadmium. Now if we want to make a P-type, then we have to replace cadmium by, now we have to go to another side, copper, silver, gold. Okay. Or we replace tellurium by, we have to go to left side by phosphorus, arsenic, antimony, etc. So I can make an n-type and p-type cadmium telluride both, and I can make an homojunction of cadmium telluride. And as I mentioned, that people have started research of cadmium telluride solar cell with homojunction. Exactly they did like silicon, okay, but it did not show very good efficiency, okay. Another way to make a p-type cadmium telluride is to create a or remove a cadmium from cadmium telluride crystal. If you remove a cadmium atom from cadmium telluride crystal, you actually intrinsically you make a p-type cadmium telluride, that one should remember. However, it is not very easy, you know, intrinsically creating a vacancy in the material. It requires some kinds of synthesis process which you know beforehand that this synthesis process can lead to vacancy in cadmium telluride and make a p-type. Better is you use the dopant as I mentioned here, okay. So let me go to a brief history of CDT solar cell, and I will come back with another information that how the efficiency of the CDT solar cell is improved with time. But if we look at the brief history, the CDT actually started way back in 1950, okay. So that time silicon solar cell technology was more or less known to people, and then they thought to bring the CDT, that is compound semiconductor, and then it was started with PN homojunction, okay. As I mentioned the beginning, it was the cadmium telluride solar cell was made as homojunction solar cell. In 1960, people have started making a heterojunction CDT solar cell, so which they have used an n-type CDS and p-type CDT, okay. And then in 1972, a 6% efficiency was shown in this type of solar cell, okay. That actually has improved with time, and if you see by 1991, people could able to show 15% efficiency in the heterojunction solar cell, okay. And of course, there are several methods. In 1981, the closed space sublimation method was introduced in order to make this solar cell, and I will come to this particular fabrication technique in a few minutes in my lecture. And in 2002, 16.5% efficiency was obtained by NREL, and which was recorded that time 16.5% efficiency, although recently people have made solar cell with more than 20% efficiency. So you have to note down this point that when we use a homojunction solar cell, you had only 3% efficiency, which has improved over time, and it has become 16.5% efficient solar cell. So now the question is why? What is the reason? The reason is, suppose I use a heterojunction cell as I mentioned that this is P, this is N, okay. So now P is CDT and N is CDS, all right, and this is the depletion region. Okay, so look at the band gap values of CDT and CDS. So the band gap of CDT is 1.42 electron volt, whereas band gap of CDS is 2.4 electron volt approximately. So what is the advantage? If I fuse now two semiconductor with such a high, you know, band gap of 2.4 electron volt with 1.42 electron volt, what I am gaining? What I am gaining is that absorption of photon, because you remember we have already discussed that electromagnetic or solar spectrum is spread over a large frequency range. That means a large energy range. And as I have shown previously, that you need photons whose band gap, whose energy should be almost equal to the band gap energy of the material. So if I consider a 2.45 electron volt material, it actually tries to absorb lot of the photons which are high energy. Okay. And if I consider 1.42 electron volt material, which is CDT, it absorbs photon of relatively lower energy. Okay, that means it covers a large frequency regime, and therefore the absorption is very high. And this actually gives us the advantage, and this is the reason why people, when started with homojunction solar cell, they only saw only 3% efficiency, whereas for heterojunction solar cell they could, in 2002, the record efficiency of 16.5% were shown. Okay, and then we will see that efficiency has enhanced with time in recent times. Okay, so let us now look at the configuration of the solar cell. So the solar cell, now what I have shown you, the heterojunction solar cell, in one side it is CDT, or P type is CDT and N type is CDS, and now with this absorbing material, or these are the material which are the basic materials of the CDT CDS solar cell, how one can make a solar cell configuration. A typical configuration is shown here. So if you look at that, there are several layers here. So at the top is glass, and then the second one is TCO, that is transparent conducting oxide. Then you have a thin CDS layer, okay, as compared to CDT, and CDT is a layer which is, if I just note down these layers here, CDT is the layer which is actually the absorbing material, and then finally is the contact, back contact. Okay. So now let me tell you about this individual material component of this basic configuration of CDT CDS solar cell. So this particular configuration is known as superstrate configuration. Okay, superstrate configuration. So what is superstrate configuration? It means that when light comes, it falls through the glass. Okay, it doesn't directly come to the CDT material. It comes through glass, and then it passes through TCO, and then CDS, which is also known as window material, then it comes to CDT and CDS interface. That is called superstrate configuration. Now, in this configuration, actually all the materials like transparent conducting oxide, like CDS, like CDT, they should be grown on a particular substrate. Okay. So the first thing is that what we require is a substrate. So the material which are generally used for substrate are glass material, particularly soda lime glass material. Okay. And one can coat transparent conducting oxide, which is the second layer of the solar cell or TCO, very nicely on top of the substrate. Okay. So the second material is transparent conducting oxide or TCO. Some of the popular TCOs which are being used in solar cell and many other fields of optics and optoelectronics are like indium tin oxide ITO or indium doped tin oxide. So ITO is basically, if you look at chemical name, is indium doped tin oxide. And then second is FTO, which is very popular these days. It's a very good, transparent conducting oxide. This is fluorine doped tin oxide. Another very popular material these days are AZO. This is aluminum doped zinc oxide. Zinc oxide is also a wide bandgap material. So people are using this, transparent conducting oxide, which are just coated on top of glass. You can see glass, you may see at the top and tissue at the bottom. Actually, when it is grown in different manner, in opposite manner. So you have glass substrate at the bottom. On top of that, you have TCO, which is either of these three. Okay. So now the question comes, why TCO? Why we need a transparent conducting oxide? What is the importance of transparent conducting oxide in solar cell? The importance is transparent conducting oxide has two important properties. One is high optical transmittance, around 80 to 90% optical transmittance. Okay. And second is low sheet resistance. Third one is CDS itself, which is also known as window material. So CDS I already discussed, its band gap is around approximately 2.4 electron volt. Okay. So it is high band gap material, so a lot of photons falls on CDS and comes to this interface CDS and CDT. And the fourth material is anyway CDT, which is our absorbing material, which I have already discussed about. Okay. So if I look at from this configuration, I have a thin CDS and then a thick CDT, and then finally we have a metal contact here, back contact you can say, either molybdenum or gold. So the entire solar cell is configured. Okay, now when we have this type of solar cell structure, okay, how this, the band gap, or how this p-type CDT and n-type CDS, when they are brought together or joined together, how this energy band diagram looks like, it is important to understand. Let us look at energy band diagram. Okay. So it is heterojunction again. We remember that one is higher band gap material, that is CDS, and another is relatively lower band gap material, that is CDT. Okay, so this is P CDT So I have a step here in the enlargement diagram. Why this step? Because now I have a material that is NCDS whose band gap is higher than PCDT. So this band gap is 1.42 electron volt and this is 2.4 electron volt. Okay, and now I have another material here whose band gap is even higher. Suppose I consider it as AZO, that is aluminum dope ZNO that I have discussed. Its band gap is 3.3 electron volt. So now if we look at how light falls, here this is the direction of light. So light falls here. So it finds a very large band gap material. So most of the frequencies of light will be transmitted through. That is what I told you, the importance of TCO materials. So light actually goes inside that, and then it finds a relatively higher band gap material, that is CDS. Its band gap is around 2.4 electron volt. So lot of light goes inside that because there is also higher band gap as compared to CDT, and this in the interface it actually generates electron. This electron goes up, okay, and they make photo generated electron hole pairs. So this is a basic mechanism of CDT, CDS solar cell. Okay. So now the next point is that how one can fabricate this solar cell. If you remember, when we discussed about silicon solar cell, we had shown a very involved fabrication technique where we have different production lines starting from sand and then up to silicon material and then up to module. So here I will discuss mostly about what are the thin film technology process that had developed over almost 3, 4, 5 decades, and people have made very good CDT and CDS material in order to achieve a thin film solar cell made up of CDT and CDS. So let us look at the fabrication techniques. So when we talk about the fabrication techniques or the thin film deposition techniques, broadly they are by two processes. One is physical technique or physical deposition, another is chemical technique or chemical deposition. So when we consider physical deposition, the main the process of physical deposition is that you choose some material which you want to deposit. Okay, in this case it is CDT suppose, and then somehow you evaporate this material or you ionize this material, okay, and then keep some substrate or keep some other material on which they can go and condensate or nucleate on that substrate, okay, and form a thin film. So we will discuss mainly about physical deposition technique, and out of various physical deposition technique, some of the techniques I will use. The first technique which has been used for deposition of CDT, so CDT material, is closed phase vapor transport technique or CSVT technique. So before I talk about CSVT technique, let me just tell about what is evaporation or evaporation of a material, because many laboratories you will find in student laboratories also, they do an evaporation method in order to grow a film. So what generally is done in an evaporation method, actually material is taken and it is kept on some boat and then it is heated somehow, electrically it is heated. And then a substrate is kept at the top at certain distance, and then when you heat this material, they are evaporated and they get deposited on the substrate. So, just let me show you the schematic. So, if you have a boat here, you take some material and then you heat it. So, this is evaporation flux, and then there is a substrate material where this evaporation material goes and form a film. Sometimes you need to heat the substrate material, sometimes you don't need to heat the substrate material. Okay. So, this is a very basic or fundamental process that one follows when one starts with a physical technique to grow a thin film. Now, when we talk about CSVT technique, it is slightly different from evaporation, almost following the same evaporation method which we have shown or I have drawn, but instead of evaporation it directly sublimates the material. Okay. And therefore, one requires a little bit higher temperature in order to sublimate the material. So, how it is done? A CDT is kept. Generally, you can see that this is a source and this is the substrate, okay, and then there is a graphite board. Well, let us say you place CDT on top of graphite board, and then through this electrical resistance path, a high temperature is generated on the source, okay, which is kept on the graphite board, and due to this the material gets sublimated and they get directly deposited on top of the substrate. However, one requires a low pressure environment in order to grow this material, and typically pressure is about 10 to the power minus 6 torr. Okay. So, one needs to evacuate. So, entire the CSVT chamber, it is kept in a vacuum chamber or it is evacuated by appropriate pumps. Okay. So, generally when we coat CDT material on substrate by this technique, they are thick film with large grain size. Okay. So, in order to make thick film, if it is required that you have to make a thick CDT film and you use it in solar cell, you use a technique which is CSVT. But there are other technique which can be controlled in much better way as compared to CSVT. And why we need a controlled way? Because suppose I don't want a 500 micrometer thick film, I need a 500 nanometer film because I want to make a solar cell of very low dimension. Then I need much better and controlled way of deposition. So, one such deposition is sputtering. So, let us see what is sputtering technique. So, how does it happen, the sputtering? Sputtering is a process by which any energetic ion, when it falls inside a material, it actually takes atom or atomic species out of this material. It gives energy to the material and then some atomic or ionic species come out from the material, that is known as sputtering. So, you know about photoelectric effect. What is photoelectric effect? Photoelectric effect is a process where photon strikes a material and electron comes out. Okay, that is called photoelectric material, which was discovered long back. Sputtering is a process where the photon does not come, it is any energetic ion ion, and then there are atoms in the material, okay, and this it gives energy to one atom. So it is a collision process. So we all know that when two bodies collide each other, there is a transfer of momentum, okay. So we have solved it in school level, that how energy momentum conservation can be established in a simple collision process or elastic collision process. So there are some other elastic collision process. Continuously this elastic collision process takes place. So there is an elastic collision process which creates a kind of collision cascade. You can see that lot of collision takes place. So different arrows actually shows different collision cascade, okay, collision cascade. So what is the result of this collision cascade? The result of this collision cascade is that some atoms which are on the substrate, on the surface of this material, they gain energy which is more than the surface binding energy of this material. So if their energy is more than the surface binding energy of this material, they come out of this material, and that is called sputtering, or these are sputtered species. So they may be in atomic form, okay, or few atoms together, or they can be in ionic form, positive ion, negative ion, depending on which material we are talking about, okay. So this same process is used in the growth of CDT. So how one does is sputtering? If you look at this system, so this is target. So target is your CDT material, okay. So you keep CDT material as a target, and then you apply a power. This is actually cathode and substrate is anode. Now this is a cathode anode configuration, and you apply a power. This could be a DC power. You can also apply a radio frequency power, okay, between this target and substrate. So when you apply this power, DC power or radio frequency power, what happens? The gas which is coming here, generally this is neutral gas, neutral, like argon gas is most popularly used. Argon is neutral, okay. Sorry, not neutral, what I mean, it is inert gas, so that it doesn't react, okay. So an inert argon environment you create here, and then when you apply power, these argon gas atoms are basically cracked in this power. So they form ionized state of argon. So when there are free positive ions and electrons, we call them plasma. All right. So plasma are basically energetic positive ions, free, and electrons. So this plasma, it contains lot of argon ions, which are same as the energetic ion which I have used here. Okay. So these argon ions, they actually now interact same. So these are basically argon ions. They interact with, say, now CDT. Now this is CDT, and then they do a elastic collision process, and then series of collision or collision cascade. After a collision cascade takes place inside this target material, CDT are basically sputtered out, and then they go and they get deposited on substrate. So as I mentioned, that this process is much controlled way. Why it is much controlled way? Because you have different parameters to play with. What are the parameters? One is gas flow rate. You can change the gas flow rate. Once you change the gas flow rate, you have less number of argon ions or less density of plasma. When you have less number of argon ions, your sputtered CDT number will also be less, so that if you want to reduce the thickness of the film, you can have a lower gas flow rate. Okay. This is one parameter. Another parameter is the power which you use across cathode and anode or target to substrate. If you give very high power, the density of plasma may enhance, and then the thickness of the film can increase. But if you want a lower thickness, you reduce the power, and then your sputtering rate will be decreased, and your film deposited on the substrate will also be of smaller thickness. So generally, for nano dimensional film, when I talk about nano dimension, there say few tens to few hundreds of nanometer dimension film with nano dimensional grains. You know, all materials have crystallites or grains, nano dimensional grains. When there is a requirement of such material for your solar cell, you can use this technique, sputtering technique. Okay. Similarly, another technique is laser ablation. So what is ablation? Ablation is different from sputtering. So what happens in ablation process, that instead of energetic ions, now photon falls on the material. Okay. So when I talk about photoelectric effect, it is photon falling on a material and then electron coming out. Here photon falls on a material, this material, and then the material is ablated. Ablated means these photons actually it gives energy to the electronic subsystem of this material. It's a very rapid process. So laser you shine, immediately it goes inside the material and then it excites the electrons of electronic subsystem. So when electronic subsystems get excited, they go to slightly higher temperature, okay, as compared to the lattice which are there at lower temperature. So there is an energy transfer to phonons or lattice. We call it lattice subsystem. And then when energy get transferred to the phonons or lattice, they get energy and they go to high temperature. And because of this high temperature, they actually come out of this material, or we call it ablation. So they come as a chunk material or ablation. So it is different from sputtering. In case of sputtering, it was just elastic and elastic, you know, the collision process, and here it is basically the excitation of electronic subsystem followed by coupling of energy from electronic subsystem to phononic subsystem, and then the temperature rise in the phononic subsystem and then coming out of the material as a chunk by ablation. So this is what is happening here. So when laser comes, it shines your source, which is a CDT material, and then it sublimates, you know, or ablate, and because of this ablation, lot of CDT material as chunk, they go to substrate and deposit as a film. Okay. Here also you have different controlling parameter, like laser power you can control, laser intensity you can control. Okay. And therefore you can have a very good controlled way of deposition of the CDT film by this technique. So generally, typically when you want to deposit a few hundreds of nanometer to few micrometer of grain size, say few hundreds of nanometer to few micrometer, you use this technique. So what we have shown that these three techniques, CSVT, sputtering and ablation, these three techniques, they are actually all laboratory based techniques. Okay, so in your laboratory you can do and you can grow film. You do not require a very big, the industrial support as it is required for silicon. Okay, in your laboratory you can grow CDT film with different dimension as per your choice, different dimension and different grain size, and this is the advantage of the fabrication technique of CDT. And now I'll just discuss one technique of growing CDS film. Okay, so people have adopted various techniques, various chemical method, but finally it has been shown by different research and development process that chemical bath deposition is a technique which is a very standard technique for growing a CDS film. So what is chemical bath deposition technique? Chemical bath deposition technique is a technique where a material is formed from its aqueous state to solid state directly. Okay, so how one can do it? So you can look at this particular configuration. You have some water bath here, okay, and then there is a reaction bath. So what is this reaction bath? In this reaction bath you need material containing the elements which you require. So in CDS you have two elements, one is cadmium, another is sulfur. So what I require in the reaction bath, I require a material which contains cadmium. So CdSO4 is used as a source of cadmium and thiourea is used as a source of sulfur. And in the reaction bath you make this complete solution of these two. Okay, and then this is the substrate, this is the substrate and this is the substrate holder, and then you have to go to slightly higher temperature, not very high temperature, maybe around 100 degrees centigrade or less. So if you remember that when we discussed about CDT, CDS solar cell, we always considered CDS at relatively much thinner. Okay, so it is few nanometer, 200 or 300 nanometer film, and you can have a very well homogeneous deposition of CDS film using this technique, CBD technique. So what I have discussed now with these four techniques, I have shown that you can make a CDT film and a CDS film whatever thickness you require as per the requirement of your solar cell or this heterojunction CDT, CDS solar cell, and these are all grown on TCO coated glass that was already ready with you. Okay, so if you look at again the configuration of this which I have already discussed, you have a glass which is a substrate, on top of that you coat TCO or transparent conducting oxide. Okay, on top of that you coat a very thin CDS layer which is window layer, that is of say few hundred nanometer thick, and then on top of it you coat a CDT layer which may be a micrometer thick film. Okay, so now the fabrication is done. So your entire, and of course that you have to add a layer, the back contact layer of molybdenum or gold. You can just evaporate molybdenum and gold, you can make a back contact layer. Okay, so your solar cell is ready with this configuration. Now there is a question: when you make these materials in this manner, say CDT or CDS, what you have looked into? Remember, there are two things which we always want to discuss. One is the thickness, another is grain size. Thickness basically decide what is the absorption. So if you vary the CDS layer thickness, you can tune the absorption of light. This is the advantage that I have already discussed. But what is the importance of improvement of grain size? If you have to make a material of very good quality, we should always remember that this material should form a very good crystallite forms. That means there should be a well developed crystallites or well developed grains. Suppose this material is amorphous or suppose this material is grainy, there are a lot of grain boundaries associated in this material. Then what happens when electron moves? They always get scattered from this grain boundary. This grain boundaries act as, a scattering center. It is not good for solar cell. You have to grow the crystal so that when the electron moves and it goes to outer circuit, it does not get such hindrance, or it should not get, scattered back by the grain boundaries. And now we look at the circuit parameters. As I told you, whenever we discuss any solar cell, we should always look at the circuit parameter. So what are the circuit parameters that we have learned from our previous lecture? One is VOC, that is open circuit voltage. So when you use H deposited cell, this open circuit voltage is around 646 millivolt, and then when you use air annealed CDS, the open circuit voltage is not enhanced much, it remains almost same. But when you treat it with CDCl2, there is an enhancement in the open circuit voltage. Come to short circuit current density. When in case of H deposited film, it is around 19.2, and when you annealed it, it is even reduced. Okay, but when you make a CDCl2 treatment, you can see that the short circuit current density has enhanced significantly. So similarly, fill factor is reduced in AR and in film, and it is significantly increased in case of CDCl2 treated film. And then finally, efficiency, which you start with 6.48%, when you anneal at CDCl2 treated film, it is 12.4%. Okay, so that means the CDCl2 treatment is involved in the CDS CDT solar cell technology. And then of course the series resistance, okay, and shunt resistance, that also one should look into. The series resistance, as we have discussed previously, in the ideal case a solar cell should have zero series resistance. Okay, so if you look at the series resistance, it is 8.62 ohm centimeter square, which is actually decreased drastically, and it has become 4.76 when it is treated with CDCl2. And RSH, that is shunt resistance, okay, which the ideal case, as I discussed in the previous lecture, it should be infinity. That means you should have a higher shunt resistance, and this you can see that the H deposited cell has 254, where it is CDCl2 treated is 2375. The value has been almost enhanced 10 times. That means you are going to a much to a cell which is more towards the ideal solar cell. Okay, so this means that CDCl2 treatment and with annealing, you can have a much better performance of the CDT CDS solar cell, and this is a regularly used the process in the technology of CDT and CDS solar cell, okay, heterojunction solar cell. Okay, so now let me just look at what are the efficiencies people have recorded so far. So you can see that 15.8% efficiency is seen in 1993, 16.7% efficiency was reported by NREL in 2001, 17.3% efficiency was shown by a company called First Solar, and then 18.3% in 2013 by GE Global Research, 19.6% efficiency was shown again by GE Global Research, and 20.4% in 2014 by First Solar, 21% in 2015 by First Solar, 21.5% again by First Solar, and by 2016 the First Solar had shown an efficiency of 22.1%. And this is a kind of the maximum efficiency which have been reported so far in case of CDT CDS solar cell. And then of course, as I mentioned in my introduction, that if you can make a multi-junction kind of solar cell, you can have much higher efficiency. Okay, this is what we will come later. And now let me just show you that one typical solar panel. It looks like the same solar panel which we have shown in case of silicon solar cell. So commercially, these cadmium tolerated solar panels are available, and people have demonstrated, industry have been using the solar panel for production of power. Okay. So let me summarize what I discussed in this lecture. So first I discussed about the shortcomings of silicon solar cell. Okay. So what we have seen this silicon solar cell, the disadvantage is that due to poor absorption or less absorption, okay, silicon solar cells are very costly because one requires quite thick silicon wafer. And when we talk about thick silicon wafer, we basically introduce a lot of materials, and as I have discussed in my previous lecture, lot of the production lines are involved in silicon solar cell. Second, what we have discussed is wide bandgap material is thin film solar cell. So there are several wide bandgap materials as I have shown, and some of the wide bandgap materials I will discuss in my next lecture. So one typical wide bandgap material, that is CDT, has been discussed in this particular lecture, okay, whose band gap is 1.42 electron volt. It is relatively wider band gap material as compared to silicon, and also it is a direct band gap material. Therefore, its absorption is much higher as compared to silicon, and therefore the thickness which we require for CDT is much less as compared to silicon. And then we have discussed CDT, CDS as heterojunction solar cell. I showed you what is the configuration of CDT, CDS heterojunction solar cell. Okay, before that I just told you about the importance of heterojunction solar cell. So when you have a p-type CDT and n-type CDS, where CDS is much higher, the energy band gap, which is 2.4 electron volt, and in CDT it is 1.42 electron volt, we have an opportunity to absorb a good number of photons spreaded over frequency or energy or wavelength. Okay, this is the advantage, and I have also shown you the configuration. So when we make a CDT CDS solar cell configuration, we always remember that we take a glass substrate, on top of that we grow a TCO material, on top of that we grow a thin CDS material, okay, few hundred nanometer, and then on top of that we grow a relatively thicker CDT material, which is the absorbing material of few micrometer, and then we have a back contact, okay, molybdenum. And this entire configuration is known as superstrate configuration. I also discussed or shown that how this energy band of this heterojunction solar cell looks like, okay, and how absorption of photon takes place in this heterojunction. And finally, we have discussed different fabrication techniques of CDT. In CDT, I discussed three physical techniques. One is CSBT, second is sputtering and ablation. And what I showed you that using this technique, one can have a very controlled way of deposition of CDT. One can have varying thickness and varying grain size. And then, of course, when you treat it with CDCl2 and annealing, you can have very well developed crystallites, well developed grains. And similarly for CDS, you have another technique which I have discussed, that is CBT technique, and the CBT technique can vary, can grow. By CBT technique, one can grow very precisely the film, CDS film, whatever you require for CDT, CDS solar cell. Okay, and I also told you about how the efficiency has improved over time, and different companies, different laboratories and researchers have reported in the literature.